In this lesson, we're going to go over a few more examples, and specifically, we're going to talk about the difference in carbocations. And so, if you guys recall from our last lesson, there are four possible situations in which resonance can occur. A lone pair adjacent to a multiple bond, a positive charge adjacent to a multiple bond, a lone pair adjacent to a positive charge, or a radical adjacent to a multiple bond. And so, we'll go ahead and do an example here. And we'll start with this structure here. And so let's take a look at which of these four possible situations for resonance we are on number 2. So a positive charge adjacent to a multiple bond. So if we do our numbers 1, 2, 3, we see that the bond between 2 and 3 becomes the bond between 1 and 2, and then remember, two things happen in resonance in pairs, and so the positive charge switches over to carbon number 3. And again, we don't draw the arrow for the positive charge because the positive charge is an absence, and so you can't draw an arrow from something that is absent, essentially. And so here we are. Here's a new structure. Positive charge has now moved over. But now we recognize we have a very similar pattern. We still have a positive charge adjacent next to a multiple bond. Now you can go two different ways. You can go backwards and, let me draw this a little bit better. You can go backwards and then reach the structure we started at, or you can essentially go this way. And so same thing, 1, 2, 3. The bond between 2 and 3 becomes a bond between 1 and 2, and then that positive charge goes on to carbon number 3. And so I'll draw our new resonance structure. Now, we have 3 resonance structures. There are no more positive charges next to, multiple bond next to the positive charge, unless we want to work our way backwards and back up to the structure above on the right. And so we don't want to do that because we've already essentially portrayed that structure above. And so these are our 3 structures. Now we have to determine which of these three structures are the most major resonance contributors. And so we see that there's a positive charge on the same atom in every case. So all structures have a positive carbon. So they're all equal in terms of having a positive charge on the least electronegative atom, right? And so that's not going to be what decides the essentially major contributor in terms of our resonance. And so instead what decides major contributor is the type of carbon that the positive charges on. And so this carbon is called a tertiary carbon. Why? Because it has 3 carbons attached to it on around it, right? And so we have a carbon right here. Let me go ahead and in a different color show those 3 different carbons. 1 carbon, 2 carbon, 3 carbon around this central carbon, which we'll notate in the blue. So that central carbon is going to be a tertiary carbon, right? And so let's look at the next carbon in the next structure. And so we'll show 2 carbons around this central carbon. We'll notate it in yellow so we can see the difference. And that's going to be a secondary carbon. And so we move along to the last structure, and we see that, go ahead and put this back in, and let's go ahead and show it in green. This will be the carbon, and we have only 1 carbon attached to it, and therefore that will become a primary carbon. All right, and so the difference between these 3, again, are the number of carbons surrounding it. So on the upper left, we have essentially, in blue, a carbon surrounded by 3 carbons, and so it becomes tertiary. upper right, we have 2 carbons surrounded by it, so it's a secondary carbon. And then lower right, we have only 1 red carbon next to it, or 1 carbon attached to the green. And so that green carbon gets a primary designation. So which of these are most stable? Well, guess what? Something we haven't really talked about yet, but the carbons in red are electron donating. They're donating electron density into that positive charge. So if we look at the structures of the upper left, we'll notice that these are carbon groups, and because they're carbon, they're donating their electron density slightly, ever so slightly, into that positive charge, right? And so because there are 3 carbons on the top structure that are donating, it's going to be more stable than a carbon that is essentially donating, or excuse me, a carbon that is being donated to by only 2 carbons. And then lastly, this is being donated into by only 1 carbon. And so this is super, super important. Why? Because what you're going to see is that a tertiary carbon is going to be more stable than a tertiary carbocation. It's important to emphasize carbocation is going to be more stable. Get this in black than a secondary carbocation, which is more stable than a primary carbocation. Right, and so of these structures now, what is going to be the major resonance contributor? I'm going to go ahead and in blue, I'm going to circle or put a square around this molecule, and we'll label this major because the tertiary carbocation is most stable of the 3 structures. All right, and so that's going to be the major resonance contributor. Now, let's look at a slightly different example with similar principles, but it's going to be different. So here is another example. And this time, instead of a positive charge, we're going to have a negative charge on this carbon. Right? And so what we have here is essentially a negative charge adjacent to a bond. And so if we look back at our 4 possible situations for resonance, we see that it will be number 1, right? So a lone pair adjacent to a multiple bond. So that's what we have here, a lone pair adjacent to a multiple bond. So what's going to happen, and I'll go ahead and actually put this in. Let me choose a different color. Let's see. I'll put it in blue, actually. We'll just go with blue. All right, and so what happens is these lone pairs, you can draw the arrow from the lone pairs or from the negative charge. It does not matter, just one though at a time. So those lone pairs are going to drop down. And so if we do our notation, this being 1, that being 2, that being 3, essentially the lone pair that was on 1 becomes a bond that is on 1 to 2, and then the bond that was essentially from 2 to 3 becomes a lone pair on 3. So I'll go ahead and highlight that, and then we'll go ahead and draw our resonance structure. Again, the double-headed arrow, and let me go ahead and draw the backbone. And now I'll go ahead and put the blue. Lone pairs became a blue double bond, and that double bond becomes essentially a lone pair now. And so this is the structure that we have. This would be designated a negative charge, and then we still have a double bond neighboring it. Now again, we're back to that same type of resonance structure, which is a lone pair adjacent to a multiple bond. Now we can go back the way we came, or we're going to go a different direction by dropping that lone pair down to form a bond, and therefore kicking that double bond onto that we'll say carbon. And so I'm going to actually put this in yellow so we can see it. And so when we do our resonance structure, we're going to go ahead and I'll draw the backbone out. And now I'll go ahead and take this, and I'll take a yellow, and I'll put the blue there, right? And so now we have our negative charge around this final atom. And so we have to compare these three structures to figure out which one's major. Now, in the previous example, we showed that a tertiary carbon is more stable, a tertiary carbocation is more stable than a secondary carbocation, which is more stable than a primary carbocation, right? And so if we look at this, we're going to see that we have a, we'll say, I'll go ahead and put the carbons here. Now we have a tertiary carbocation, and I'll use blue again to indicate this carbon. It might be a little confusing, so I might go ahead and go with green here, the central carbon. So this central carbon is tertiary, but it's a tertiary anion, right? So it would be a carbanion, right? And so the structure to the upper right has two carbons surrounding it, and I will put it in blue. So that carbon in the middle between the two is going to be a secondary anion. So a secondary carbanion, right? And then lastly, the carbon here at the bottom, which I'll put in yellow, left with no choice. And there has one neighboring carbon, and so therefore it is a primary carbanion, right? So we have tertiary, secondary, primary. So let's go ahead and take a look at this and compare. Now, we said carbons are slightly electron donating into that positive charge, right? So if we have these same carbons essentially donating into a negative charge, that's not going to be ideal. We already have electron density in there, right? So donating into a negative charge is actually going to be not a good thing for us. And so we don't want that to happen. So the less carbons we have donating, so in this case, the bottom right structure, we only have one carbon donating into the negative charge for that electron density. And so we have the relatively more stable than the other two structures, which has electron density being pushed in from there, right? And so again, we don't like that. That's not a good thing. And so the best carbanions are going to be primary because it's the best of a bad situation, right? And so let's go ahead and rank these. We have a secondary in blue. And then lastly, we have a tertiary, which we designated green. Right, and so it's very important to note when it comes to positive charges, the order of stability. So I'll go ahead and write more stable. The order of stability for a carbocation is inverse to the order of stability for a carbanion. All right, so let's actually stack these two above each other. And so in carbocations, you have a positive is greater than tertiary carbocation is greater than a secondary, which is greater than a primary. For carbanions, again, the opposite is true. So you have charge is more stable than a secondary negative charge, which is more stable than a tertiary negative charge. So this is for both cations. This is for carbon. Right, and so if we go to these three structures, based off of that, we know that primary carbanion is most stable, so this is going to be the major resonance contributor. Right, and so that becomes super important. Why? Because when we draw our resonance structures, we'll know which one is contributing more, and these are questions that are high yield that are asked of you again and again. And so it's super important for you to have that down. Now let's do one last example, and this time of radicals. So we may not have gotten to the radical chapter yet, but I think it's very similar to these, so it's good to expose you ahead of time for that. So this is example number 3. And we're going to go ahead and make it very, very similar to the first structure. Now, if we go up to our possible situations for resonance, this would be the fourth, radical adjacent to a multiple bond. This acts very similarly to a negative charge adjacent to a multiple bond, except that there's something called homolytic cleavage. And so what happens is we draw a half arrowhead to indicate that this radical, so I'll actually play with this a little bit. I'll color the radical here green, and I'll color, so a bond is actually 2 electrons, so I'll kind of designate that with blue and yellow. So that bond is comprised of both blue and yellow electrons, just for the sake of understanding where things are moving. And so what happens is this blue electron, half arrow, just that one electron, not the whole bond, will form a bond. Let's number this 1, 2, and 3. It will form a new bond between 1 and 2 by combining with the electron, the radical on 1. And so what you'll get is a resonance structure that looks like blue electron there that was initially part of that bond, and then a green electron there. And so we'll draw a bond between the two to show it's now a bond. Again, these green and blue are just designations for us to understand where the electrons are going. And now the yellow is essentially a lone solitary there by itself on carbon number 3 across what our numbering designations, right? And so now we find ourselves again in a similar position where we have a radical next to a double bond, and so there can be resonance here again. And so let me go ahead and label these. We'll say this is blue, and I'll go ahead and drop down this radical with a half arrow and drop down that radical with a half arrow, and I'll go ahead and renumber these. So I'll erase my initial designations, and I'll go ahead and renumber these 1, 2, 3. So the radical that was on 1 joins an electron from the bond that was between 2 and 3 to form a new bond. Go ahead and draw this and that. Okay, and now we'll go ahead and draw electrons. And then now the blue radical is alone by itself. So these are the three resonance structures. You'll find that the radical is very similar to the negative charge example, except wherever there's a negative charge, this one right here, wherever there's a negative charge, there's a radical instead. So we started with a radical here, and so the way it moves is slightly different because of that homolytic cleavage, but the idea is essentially the same. So now let's take a look. We have a tertiary radical on this first structure. Why is that? Well, that's because we have three neighboring carbons all pushing electron density to where that radical is. So that radical is essentially unlike a positive charge. The positive charge is an absence of electrons. So when you have three carbons around a positive charge, that's a good thing because carbons are pushing electron density into the positive charge. However, a radical is electron density. When you have three carbons around something with electron density, like a radical or a lone pair, negative charge, whatever, it's not good to push electron density into where that radical already exists. It's only good when you're pushing it into where a positive charge is. So we'll go ahead and put the charge there. It's only good when there is a positive charge there. Otherwise, it's bad because you're pushing electron density into your electron density into something with already electron density. And so that's a tertiary radical. Now the next structure is a secondary radical. And so what we're doing is seeing two carbons adjacent that are pushing electron density. That's why it's a secondary radical. The reason this is a tertiary radical on the left is because there are three carbons adjacent. Here, can you guess how many, what radical this is, what type, based off of the carbon adjacent to it? How many carbons adjacent to it do I have? I only have one. I have hydrogens that are implied. However, I only have one carbon. And so this is just going to be a primary radical. And so if this is a primary radical, let's order the stability of these radicals. Stability of these radicals is going to mimic the stability of a carbocation, carbanions. And so, again, let me repeat that. The stability of radicals will mimic the stability of carbanions. Why? Because they're all electron dense, right? And so they're going to be very similar. So I'm going to go ahead and do a tertiary radical. A primary radical is more stable than a secondary radical, which is more stable than a tertiary radical. And so let's go ahead and copy this over and make one final comparison. Go ahead and move down here. And so I'll go ahead and finally draw radicals. We have a primary radical is more stable than a secondary radical, which is more stable than a tertiary radical. Right? And so by that logic, we're going to figure out which one is the major structure. And it will be the one, again, if we go in this order, primary will be most stable. And so let me designate, I forgot to do this, most stable on this side, least stable on that side. Now again, this will be super important. I'll say most stable up here and least stable up here. This will be important because it will come up again and again. You'll need to see which is the most stable structure when you're forming a mechanism, when you're doing a reaction. Again, being able to recognize that the reaction proceeds through the more stable radical will be very helpful in getting the correct answer. If you don't recognize that, what will happen is you'll form a product, on a less stable structure, and therefore it will be the incorrect structure. So it's crucial that we get this down and really get good at this.